Welcome to the third video for the power engineering module, and this will be based on three-phase AC circuits. So let's begin. So what are the three phases that we talk about? Because we had said that we will talk about this later, so now is the time. So to introduce this, let's just say that there are three wires, right? And each of them is connected to a voltage sources one end, and the three voltage sources that are now there, you have connected the other ends together into one knot. So there is one point from which three voltage sources come out, and then the other ends of the voltage sources are leading out to to three wires. Now each voltage source is at a phase difference of 120 degrees from the other voltage sources. So this is what it would look like. There would be one wire which would be carrying voltage like this, another wire that would be carrying it at a 120 degrees phase difference, and then another one which would be carrying it at another 120 degrees phase difference. Okay. Now the voltages, as you can see, as time progresses, phase 1 achieves its peak, then phase 2, then phase 3. So this is called the phase sequence, the order in which these phases are achieving their maximum. So an RYB phase sequence means R achieves peak, then Y, then B. And this means that Y must be lagging R by 120 degrees and B must be lagging Y by 120 degrees. Remember that RYB is not the order in which the phases occur in clockwise direction. This is a very common misconception. No, that's not what happens. It is the order in which the phases achieve the peak. So it's actually the opposite. Now RYB is sometimes called an ABC sequence or positive sequence. They are all the same thing. Now what is star delta? Because this will come a lot in three-phase circuits. So this is star and this is delta. Some people call this Y also. Basically, these are the three wires, right? Now, if you want to connect an appliance, a set of three appliances, there are two ways you could do this. You could either do it like we had explained the voltage sources. You could put them together and have a common point, or you could just simply connect them across the line or the wire itself. These appliances might actually be impedances, like here it is shown to be resistances, but it could be any impedance. It could even be sources of voltage or current. So like the thing we had talked about in the first slide, that was a Y connection or a star connection of voltage sources, right? Note that you could always go from Y to delta or delta to Y for impedances using the formula that we had derived. So that Y delta thing still remains here. It's true. You could do that conversion. It's legal. But the source conversions about voltage and current, they are a little more involved. So before that, we will do something called a balanced circuit. Why? Because a balanced circuit is much easier to handle. We will see how. See, if the loads are symmetrical in nature, which means that each wire feels the same impedance across the other two wires, then the currents also turn out to be at 120 degrees from each other. So what do I mean by symmetrical? Well, in the previous slide, uh, suppose RHC equal to RAB equal to RBC, or RA equal to RB equal to RC. So that would be called symmetrical load, and in this case the currents also turn out to be at 120 degrees from each other and their magnitudes would be the same. In such a situation, the circuit is said to be balanced, and most three-phase circuits are actually of this kind, and these have a major advantage. And what that advantage is that you can boil this three-phase circuit down to a single phase circuit, because by symmetry you will notice that all the things can first be converted into Y. We will see that you could always convert something delta into something Y, and then after doing that, what you could do is that you could connect all the star points of the Y, because all of them would be at the same potential. They would all be at zero, because it's so symmetric that since the voltages at the ends are at 120 degrees lagging from each other, it's like their average is zero at the all of the neutral points. So you can just connect them by a conducting wire, and now you have three single phase circuits. Additionally, it's so symmetrical that actually it is a combination of three single phase circuits which are all identical, just the fact that there is a 120 degree phase difference in each. So you just solve one circuit, add 120 degrees phase difference, and you have got the other circuits. But how do these Y delta conversions occur? How can you convert a source to Y? How can you convert a load to Y? Let's see that now. So first, let's just see this is how a balanced circuit would look like. So how do you do a source conversion? So to understand that relation, we must first understand the relation between line voltages and how they look like. So suppose that we try to define the line voltage as the voltage between any two lines. So there are the wires that were coming there. You take any two wires, you measure the voltage between them. That is called the line voltage. Now, if your phases have voltages VA, VB, VC of V at 0 degrees, minus 120 degrees and minus 240 degrees. Observe that since C is lagging B is lagging A, this is an ABC sequence, hence this is a positive sequence. Now, you could do simple phasor mathematics. You could simply take the difference of VA and VB to get the potential of A with respect to B, which is what the line voltage is, right? So, the line voltages will come out to be V root 3 at 30 degrees, V root 3 at minus 90 degrees, and VCA will be V root 3 at minus 210 degrees. Observe that this is simply the voltages that were there previously having a root 3 factor, and all of them turned 30 degrees leading. This is much easier to see using a phasor diagram, because you see this is VA, this is VB, this is VC. Now when you take VAB, so VA, now you want to reduce VB, so you take the inverse of that and then you add it. So this angle is basically 30 degrees, and this angle is 30 degrees, and this angle is 30 degrees. Okay. Now a similar operation for currents can be done. So VA was the potential of wire A, hence the IA would be the current in wire A. But what would IAB be? So IAB would be if you apply some appliance across the wires A and B, then the current that would flow through that would be the current IAB. Now observe that this mathematics won't work here, and instead you will have to take that IAB plus IBC will be IB, because we need that all the currents that are coming into a node have to add to 0. So when you do that, the same phasor arithmetic will then give you that IAB is I over root 3 at 30 degrees and minus 90 degrees and minus 210 degrees. Observe that even though instead of root 3 a factor of 1 over root 3 has come, the currents are still leading, right? So whenever you go from VA, VB, VC to VAB, VBC, VCA, or IA, IB, IC to IAB, IBC, ICA, there will be a net leading of 30 degrees that you will get. And this is where phase quantities come in. So what is a phase quantity? Now phase quantity is defined as a quantity that you measure across or through a single component. So when we have a star connection or a delta connection, these values will change. How? Let's see. So if it is a star connected sequence, you can see that the phase current is simply flowing right into the line. So the phase current is the line current, but the phase voltage is not the line voltage, because the phase voltage is VA, the line voltage is VAB. Hence, there is a root 3 factor that we had seen, and it will be leading by 30 degrees. Now, if you have a delta connected thing, the phase is simply across two lines. Hence, the phase voltage is the line voltage, but the phase current is not the line current. Instead, it is root 3 times, but then lagging by 30 degrees. Now, there is a lot of leading, lagging, and multiplication by root 3, division by root 3 going on. So, just remember this. Whenever you try to go from star to delta, you just add a 30 degrees phase shift to the leading side, right? Now, if you are taking the voltage, make sure that you multiply by root 3. When you are taking about current, make sure you divide by root 3. Alright, just keep this mnemonic in mind, that star to delta, 30 degrees phase shift to the leading. Now, here is a slide to make you help visualize what I'm talking about. So line voltage is across these two lines and appliance is across these two lines. Hence the phase voltage is the line voltage. But these two currents are getting added at this point. Hence the phase currents are not the line currents. It's their sum. Similarly, the phase current is simply flowing through the lines. So the phase current is the line current. But the phase voltage is not the line voltage. The line voltage is the sum of these two phase voltages. Hence, the current would be the sum of these two currents and hence be bigger in magnitude, specifically by root 3, and the voltage here would be bigger in magnitude, specifically by a factor of root 3. So just keep this in mind. And this node, we could tap it out and call it the neutral. Yes, that's because when we will talk about the balanced circuits, we can connect them all together. That's why I've shown that. Now, what about the power in a three-phase circuit? And power is actually very simple to calculate in a three-phase circuit, and the reason is that you could simply take thrice of the power. So when you calculate S for one phase, you could simply calculate 3 times S and you're done. You have solved the power for the three-phase circuit. There is no very big complication, but here is a noteworthy point. Be it star or delta, VLIL is always VP IP into root 3. Now, what are these VLI and VP IP? So, VL and IL are the line voltages and line currents. VP IP are the phase voltages and phase currents. So, see, if it was a star connected thing, the currents would have been the same, but the voltage would have been root 3 times. Had it been delta, the voltages would have been the same, but the current would have been root 3 times. So this always works. And since we are talking about 3 VPIP, that is same as root 3 VLIL. Now I have added a cos phi because, well, the real power has that component, right? What is phi? In any one wire, the leading of the voltage phasor by the current phasor, the angle by which the voltage phasor leads the current phasor in any one wire, any of the three wires. Since it's symmetric, it would basically be the same. Just take any one wire, take its cos, you are done. This is the basic power equation in three-phase circuit, root 3 VLIL cos phi. Just remember this. This is very helpful in calculating the power. A very big note, and this is actually overlooked at a lot of places. Whenever you are given a voltage in a three-phase circuit, it is always line to line. Okay, it does not matter if the person said that the source is star connected or something else. It does not matter. If they have mentioned a voltage, it is always line to line. Unless, of course, they are actually specifically saying that no, this is a star connected source and I am talking about the phase voltage. So VA is this. Otherwise, they are always talking about VAB. Now, if you have an unbalanced circuit, there's not much you can do. There is no symmetry. You will have to take two mesh currents and you will have to solve those for those two mesh currents, right? You will have two loops. Just apply the mesh current equation. It's not that hard, but you have no symmetry, so it's not as easy as a balanced circuit. That's all. You could simplify it for the case that both the load and the source are wire connected and I've joined their neutrals using a conducting wire. Okay. In this case, it turns into three single phase circuits and that little wire in the between that is carrying all the current back from the load to the source. In such a case, if you wanted the total S, you could simply calculate it for each phase individually and then add to get the total. How do you make this three-phase circuit? So this is not actually covered in a module, but it would interest you to know that there's something called an AC generator, and that is how you can actually make three-phase voltages. You can produce those 120 degrees lagging from each other. So this is the end for the third video. Thank you.